Welcome to qnawire.
We're given a large sphere, mass capital M of 1,000 kilograms that has a radius of 5 meters, and then we put a small test mass, lowercase m, some distance, little r away from it, and we want to know what the gravitational force is on it. So in the first case, this distance r is 5.01 meters. And that's important because it's larger than the size of the sphere, so that means that the mass is outside of the sphere. And whenever we have a case like that, where the object is not touching the first one at all, we can treat this large sphere as if it was just a point particle. That's exactly how its gravitational force will act. So this situation, we can just reduce to something like this. So we have our large mass that we just treat as being a single point particle, and it's a distance little r away from our small test mass. And so now we can just apply our gravitational force equation. So Fg is just going to be the gravitational constant times capital M times little m over little r squared, the 5.01 meters. And we can evaluate that and get 5.31 times 10 to the minus ninth newtons. So in the second case, we're told now the radius little r that we're placing the small mass is only 2.5 meters. And so that means it's going to be inside the sphere. So let's go around to this next page to look at that. So we have our big sphere, and now we're putting the small sphere inside the original one. And so now we can't just treat the large sphere as if it's a point particle. We have to account for the fact that the mass has a distribution now. And so what we need to do is treat the sphere as only having this small mass now. So a distance r, where little r here is now 2.5 meters. So we only want to consider the mass of the sphere 2.5 meters from the center. So that's the only thing that's going to be making an effective gravitational force on the point particle. All of this other part of the sphere does still put a force on it, but it just turns out that every part of the sphere is pulling on it, so the forces all cancel out. So the mass up here pulls up on the sphere like that, the mass down here pulls down on the sphere, and those two forces always end up canceling each other out. So effectively, we only worrying about this middle part of the mass. So we know the distance, but we just need to know how heavy that mass is to be able to do our gravitational force equation, Fg equals g. And then I'll call this mass inside the DAS region now, I'll call that capital M prime, since it's some different amount of mass. And then little m over r squared. So we just need to find this m prime. So I'll start with the fact we know the density of an object is just its mass over its volume. And so that means the mass of something is just its density times its volume. And so we can say then that this m prime we want to find is the density of the sphere times the volume that it's occupying. And so the density of the sphere we know is just the total mass of the sphere, capital M, 1,000 kilograms, divided by the volume, which is 4/3 pi capital R cubed. So this entire distance of the sphere, 5 meters. And then times the volume that we're only considering, which will be 4/3 pi little r cubed. So the 4/3 pi cancel out, and we're left with just m little r cubed over big R cubed. So that's our m prime. And so now we can put this into our force equation. And so we should get that Fg is equal to gravitational constant times capital M r cubed over big R cubed, and we still have this little r squared in the denominator, and we have little m up top. So these r's cancel, and we're left with g capital M r little m over r cubed. And so I've specifically left this all just symbolically because that'll make the next part much easier. So we have all these numbers now. R cubed, r is just 5. We know 1,000 kilograms is the mass of the whole sphere, 2 kilograms is the little one, and then 2.5 meters away for r. So we can evaluate this, and we get 2.67 times 10 to the minus 9th newtons. So that's less than our previous value, so that makes sense. There's less mass acting on it. But the main thing is really this result here. And so that tells us that when we're inside the sphere, as we increase little r, how far away from the center of the sphere we're putting our particle, the force increases linearly. So everything here is a constant except for little r. So as we move farther away from the sphere, the force of gravity just linearly increases. And so now, on the next page, for part B, we're asked to make a graph of what the gravitational force looks like. So just a qualitative graph. So we have the force of gravity on the y-axis, and we have little r, the distance from the center of sphere, on the x-axis. And so looking back at our equation, we can see that when little r is 0, the force of gravity would be 0. So basically we're enclosing no mass, so there's going to be no force applied. So that would just be the test particle being right at the middle, so everything's kind of pulling on it equally. So it's going to start at 0 and just linearly increase. So it's just increasing, 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 and then finally it's going to get to the edge of the sphere. So this will be at value r. So this is where it's at all the way at the edge of the sphere. And now, as little r increases, it's outside the sphere, and then we know gravitational force just goes like 1 over r squared. So as we get farther away, the force just decreases like a parabola. And so it's just going to do that forever and just approach 0 out to r equals infinity.